Good morning. I'm Sadie Forbes. I'm pre-recording this presentation from Cambridge, where I work with Professor Hagelstein and Florian Metzler. I regret that I can't be at the conference this year. Hopefully next time. So by way of introduction, our motivation to get started on this work was a desire to replicate the experiments done by Lipinski and Lipinski, in which they observed alphas from a lithium target that was being loaded with up to 400 electron volt hydrogen ions. We also felt that an ion beam experiment will be useful for an array of condensed matter nuclear science experiments that would include low-level DD fusion and low-level energetic ion emission. Here's a quick rundown of Lipinski's work. They had a large vacuum chamber, lithium target, proton gun, and charged particle detectors, the same kind that we are using. Those are Ortec silicon-type charged particle detectors. And they ran experiments at between 4 and 320 microamps that was capable of producing between 50 electron volts, and at the high end could go to 5 keV. Here's a quick summary of their results. They had a burst of alphas near 8.5 MeV. There was a 90-second burst that was sustained at approximately 157 counts per second, and that was within a 1/2 hour total observation of charged particle emission. Here's our work to replicate that. Our equipment consists of an 18-inch spherical chamber running at ultra-high vacuum. We've got an ion source at the left. We have an RGA and, of course, ion vacuum gauges, cold cathode and hot cathode as well. This is an internal layout. The beam target is shown in red and the ion source off to the left. The green lines show approximately the spread of the beam that we get from this equipment, and then the detector array, as it was in the first experiment, is in blue and facing toward the target. And this is a photograph of that. That's with the ion beam on, titanium target, and a couple of charged particle detectors that are hooked up to an MCA. Here's a discussion of our lithium results. We have not yet seen any energetic ions from these experiments. We've observed interesting artifacts involved in high loading of deuterium and hydrogen into a lithium target. With experience, we learned how to load to higher levels without overloading our pumps. This required manual control. As the target heats up, it wants to evolve the deuterium that you've gotten into the lithium very badly. And you can see during the unloading sequence, after which everything's been turned off. So in the far right-hand side of the screen, that's a view of pressure decay, and you can see that it's not at all linear. The deuterium or hydrogen want to come out in fits and starts, and we do not understand that behavior. Here's a view of a thermal anomaly that we saw in a 10-day-long experiment. Well, monitoring of pressure, I should say. I wouldn't call this an experiment, but we generally have our monitors on. And we had a temperature spike that coincided with a pressure spike. We looked at this fairly long and hard and concluded that there are almost certainly Newtonian explanations for what we were seeing, and that there's nothing nuclear happening in that experiment. So far, we have not seen any energetic alpha particles at or anywhere else with lithium. Our charged particle detectors, however, were only operating during our early experiments pre-pandemic. We ran into problems with them when we were able to resume work after the pandemic. As I showed before, we observed interesting things with pressure and thermal artifacts. And finally, we note that the Lipinskis saw energetic ions only during one experiment out of roughly 20 that they performed all told. Here's a quick rundown of our early experiments from 2019. We were motivated by Chambers et al., who worked at the Naval Research Laboratory and obtained roughly 5 MeV charged particles in an experiment implanting 350 electron volt deuterium ions into a thin titanium film with their detector backed behind the sample. We presented this in a CC, and this is just a quick review of that work. Our parameters for our experiment were 950 electron volts. We loaded for a total of 4.5 hours at a couple of different ion beam currents, and then switched over to argon for just about a quarter of an hour. And fairly early on, we saw charged particles detected on our MCA and a coincident spike in observed neutrons on the Wendy detector that sits alongside this experiment. Well, we've quoted nominal MEV values. Those are based on a single calibration with americium-241, and we don't believe that that calibration is especially accurate at the higher energies. So here's a quick rundown of the results. As I just said, small number of energetic particles. Calibration that we don't consider to be especially reliable in the range that we were seeing. Counts on the MCA and correlated in time with a neutron spike that would be well above background. Our ion count is fairly low, we think, in part due to poor detector solid angle. We've got 50 mm square detectors a couple of inches away. So that was all before pandemic, and after working on lithium for a while, it's been our intent to come back and try and get more replication of that and to try and amplify our results. So here's what we've been able to finally get up to. We adopted a different foil detector configuration for our primary detector. This is a 25 micron thick titanium target, which is held onto a copper target holder. That same holder now is used for the mount for our 2000 micron depletion depth silicon charged particle detector. And then we have a copper heatsink, water cooled, that is necessary for keeping the temperature of the charged particle detector down below room temperature. Otherwise, it gets very noisy. Lastly, we used a boron nitride heat transfer layer in order to cool everything as well as possible. We don't want to just be in contact with the detector, and we don't want to just be in contact with the target holder. Here's a calibration. This particular calibration run was using americium-241 at 5.49 MeV, and we saw a peak in our MCA at bin 1724. The source of the americium alpha source was held 2 millimeters distant from the detector surface and in an all helium atmosphere, so as to have minimal impact on energies. We saw exactly the same values in a fair number of runs, calibration runs in vacuum as well. We think the protocol for loading and trying to then stimulate phonons or induce phonons in the target are important. We typically clean our surfaces one time with 50 microamps, 500 to 1,000 electron volts, a couple of hours. Should remove oxides from titanium pretty well. We have worked loading with a deuterium ion beam at anywhere between 50 and 250 microamps and between 500 to 1,000 electron volts for between 2 to 24 hours. And working experiments that have generated interesting results seem to run in the range of 1 to 4 milliamps. Less so far does not generate any interesting results. You'll see some of that in a moment. So we have generally observed effects immediately after application of argon excitation, and that was all we saw in the 2019 work. In the work that we're doing now, we are seeing it for many hours after, and sometimes, of course, no results at all. Here's simply noise spectrum. This is looking at the detector and MCA recording for while running a deuterium loading cycle. This means that there's some heat going into the detector, and this brings the noise floor up a little higher than it would be. This is the same detector with the ion beam off, and you can see that the noise floor is down around bin number 400 rather than bin number 500. We aren't perfect in removing heat, but we don't get a whole lot of extra noise either. Here's a null result experiment run on July 18th. Our operating parameters were an ion beam at 950 electron volts, loading deuterium for 20 hours at 100 microamps, and then excitation with argon for 10 minutes at half a milliamp. And you can see that there are no interesting counts on the charged particle detector here. Here, however, we ran at a higher current argon beam. All rundown of our parameters are the same 950 electron volts. We loaded for 20 hours at only 0.5 milliamps, and then ran excitation at 1.5 milliamps for 10 minutes. And what you see here is counts that were recorded during the argon loading cycle, and there are counts at just above bin 13,000 and just below bin 14,000, and then a couple down in the 12 to 1500 range. There are also witness lines for where our americium calibration point falls and where we would expect 10 MeV to be if we believed it. Now, also from this same run, but counts that were all recorded after the power was, after the argon was turned off and everything else in the experiment was powered down. And here we see a range of charged particles seen on the detectors from upwards of around bin 3100 down to around, well, let's say anything above bin 800 is probably not noise in this experiment, and maybe things below 800 could be noise. We will be characterizing that better with time, but suffice to say that our charged particle detectors have been quite noise-free when running moderately high beam current and beam energy. So all of this, and then I want to note that these various charged particle counts seen by the MCA were seen across the entire duration of 12 hours of run, and there was still a little noise when I proceeded to run the next experiment. Here's a second experiment. In this one, we ran close to the same parameters. Well, no, not exactly. We ran different loading parameters. So still 950 electron volts. We loaded deuterium for only 2 hours, but at significantly higher current, 200 microamps or 0.2 milliamps. And then the same excitation cycle of argon for 10 minutes at 1.5 milliamps. We chalked up 2 counts in the MCA, one just above 12,000, bin number 12,000, and one just above bin number 16,000. After turning the equipment off and continuing to monitor the charged particle detectors, we see a similar spectrum to what we saw after the argon cycle in the day before's run, so ranging from about bin 2450 down again into the low ranges. And you may note that between 1000 and 1500, there are some clustered values. So there might actually be spectra there. We need to get better signals before we can call this a spectrum. Okay, conclusions. We've built and run and advanced the quality of our ion beam apparatus. We ran initial attempts to replicate the hydrogen lithium system experiment of Lipinski and Lipinski. Have not seen anything yet in terms of things that we think are nuclear. We did observe outgassing and thermal effects that were surprising and complicated the running of experiments. We would like to revisit hydrogen lithium with our new charged particle detector configuration. That will come in the future, and hopefully with better material handling, because lithium isn't that easy to work with by comparison with some other metals. We briefly reviewed the energetic ions and neutron counts that we saw in our 2019 deuterium and titanium experiment. And we've worked up a new experimental configuration with the detector close to the sample. And then in recent experiments, we've shown counts across a wider range of energies, and the current thrust of where we want to go with this work will be to improve the count rate and get something that looks more like a spectrum. I want to emphasize that after a long time and a lot of effort of trying to replicate and being stymied mostly by lack of resources, we've now got an apparatus that's working pretty well, and I think we will be generating quite a lot of new data over the coming weeks and months. And so we're quite happy about having gotten there after a long time of being shut down for various reasons. Okay, that concludes this talk. Because I can't be at the conference, please don't hesitate to contact me with questions, comments, etc. at sadie@mit.edu. And thank you for your time and attention. I will sign off and end this now.